the last talk for today will be given by Villaro Krüger from Moscow High School of Economics, and he will talk about Hilbert's Hilbert schemes of twisted quadratic curves on threefolds of type 4-1.
Yeah. And thank you to the maybe not entirely impartial organizer for letting me give this talk. So the first half of this talk, part one, I will discuss about the connections between isotrivial families. I will explain what this means, families, and automorphisms of the fibers of such families. And during the second part of this talk, I will apply this to a more complicated example. So first we will discuss some easy examples, and then we will discuss more complicated example, which is isotrivial families where the fibers will be Fano threefolds of type 4-1. I will explain what this means later, and we will discuss connections between the automorphism groups of such threefolds and the Hilbert scheme of twisted quartic curves on such threefolds. And the end will be based on some work in progress, but I still think the ideas are interesting, and there's an interesting concrete construction here. So let's start with the first part, and let me define what I mean by isotrivial family. And isotrivial family is a flat morphism between smooth projective varieties, and we want all geometric fibers, I think, to be isomorphic to some fixed smooth projective variety set. And such a family is trivial if X is just the direct product between Y and Z, and F is the projection to Y. And such a family is isotrivial.
So we want to use what type of variety?
Smooth projective.
Okay. And over field.
Yeah, over field, I think.
It doesn't matter what field.
Generally not. No. And we say that it's isotrivial if there exists some Etal cover of Y, so that some Etal cover that trivializes our family. So this is Etal, here we have X, and this fiber product should just be the direct product between X and Y prime. This is what we mean by isotrivial. And let's do an example. Example 1. In this case, our set will be the affine elliptic curve defined by y squared equals x cubed minus 1. And we construct a family over C star. Where the fiber over T will be the affine elliptic curve defined by y squared equals x cubed minus T. So these affine elliptic curves all have the same gain variance, so they are all isomorphic. And this family is not trivial. There's a quite nice argument why this family is not trivial, but probably it's more interesting if you try to think about why this family is not trivial. And if you get stuck, you can talk to me in some break. But this family, let's call it F, is trivialized by the Etal cover from C star to C star, where we send T to the power of 6. And this is because after base change, So let me draw the diagram here. C star, E, X here. And this becomes the direct product here, because when we take the pullback of this family X along this cell cover, the fibers will look like the affine elliptic curve in the form y squared equals x cubed minus t to the power of 6. And we can just make a change of variables. We can write y equals y times t cubed and x equals x prime times t squared. So the family is trivialized. And using this family, we can construct automorphisms of this elliptic curve, because this is also a homeomorphism of groups. And the kernel of this homeomorphism is Z mod 6Z.
Yes, this is some mistake in definition.
Yeah.
It should be Z multiplied by X on the left. Isotrivial et al. Z multiplied by X.
No, X is the total space.
Yeah, but there
So-
you write E
Yeah,
multiplied X.
thank you.
So there.
Yeah.
Okay.
Yeah, the multiplicative group here. So we have a projection here to E. And in fact, this group acts on these fibers, and they act as follows. We have an isomorphism between the affine elliptic curve E and the fiber. So this was F, let's call this F prime, let's call this E prime, the fiber over 1, which by commutativity here is canonically isomorphic to the fiber here over 1, which again is canonically isomorphic to the fiber of F prime over the 6th root of unity, or the image of any point here, which then by projection to E here is canonically isomorphic to E. And if you write down everything and you look at the way we made a substitution of variables, you will see that this automorphism is in fact defined by x comma y maps to 3rd root of unity multiplied by x minus y. And you can see that this will still be a solution to this elliptic curve. It will still lie here. And in fact, this generates the whole automorphism group of this elliptic curve. So from this isotrivial family, we obtain, in this case, we obtain the whole automorphism group of the elliptic curve. Often we will just obtain some subgroup of the group of automorphisms. Now let's discuss how we can go the other way. So how, given some, okay, this is, so just how given some group of automorphisms, we can obtain an isotrivial family. So automorphism to isotrivial family. So say we want to construct some isotrivial family where all the fibers are isomorphic to some smooth projective scheme set. Set here. What we need is some finite group T that acts on Z. And we need to construct some family over some base B. And we need an action of G and the base, which should be free. Ideally, B will also be a group scheme. And then we can, then we can construct this commutative diagram. So we have B times Z here, and we have the projection to the base. And then we take the quotient of B, and we want B to be a projective, smooth projective variety so that we can take this quotient, B quotiented by G. And here we take the quotient of the product. So G also acts on the direct product. And this construction is basically the same as the construction of elliptic surfaces. So this is a very general classical construction. And let's try to use this to construct some P1 family.
Can you please repeat what is Z and what is B?
So C is the fibers. We want to construct some family, isotrivial family, where all the fibers are isomorphic to Z, C. And B, it's the base, and here's some finite group. So we construct a family over B with all fibers isomorphic to Z. So in that case here, Z was the elliptic curve E, and B was C star, and G was Z mod 6Z. So I would like to construct some isotrivial P1 fibration. And the group that I would like to use is the Klein foregroup. Does somebody have some ideas or know how the Klein foregroup can possibly act on the projective line? So it should act by some involutions, because all the elements in this group have order 2.
Free and move.
Yeah. And we want them to. So the Klein foregroup is generated by 2 elements which commute. So if we can find 2 involutions which commute with each other, then we are done.
Can you just act on the homogeneous coordinate?
Yeah. So say the first involution I1 can act, how could it act, for instance?
Mapping xy to minus xy.
Yeah. And minus xy. And the other involution, how could that act?
X minus y.
X, y. So that would be the same.
Yeah,
because it's homogeneous.
So yx.
Yeah. And these 2 involutions commute with each other. And in fact, this is the only faithful action, because you can make some projective transformations that make the involutions like this. All right, the next step to use this construction is to find some base where the Klein foregroup acts freely. So what could be some smooth projective variety where the Klein foregroup acts freely? Well, if we take elliptic curves, they look like toruses. Then we can translate them, and we have a 2-torsion translation group. So some genus 1 curve, call it gamma. It looks like a c squared modulus some lattice, something like this. So it's some torus c squared, c modulus some lattice, and we can act on it by a translation. All right, so let's do it here.
So we like translate horizontally and translate vertically.
Yeah. And then we construct this family. So here we start with P1 times the curve gamma. And then we project it to gamma. And then the quotient of gamma by this 2-torsion translation group is canonically isomorphic to the group, no, not the group, but to peak 2 of gamma, to this component of the Picard screen. So this map is defined by taking a point P and sending it to the divisor class 2P. So this is an Itzel map of degree 4. And here we will have the quotient of P1 times gamma by the Klein foregroup. this will be some non-trivial P1 fibration. And because this is a one-dimensional smooth projective curve, it will have to be the projectivization of some rank 2 bundle. And I'm not sure how it's obvious that, so it's not trivial, but I'm also not sure how it's obvious that it's not the projectivization of the direct sum of two different line bundles, but so there's, but the third option is the projectivization of the only stable rank 2 bundle. And there's some slightly complicated argument might have to be the projectivization of this rank 2 bundle. And in fact, this quotient must be isomorphic to the symmetric square of this curve gamma. So pairs of points on gamma. It can't be anything else. There's no other candidates, but I'm not entirely sure what would be a simple description of this map from P1 times gamma to the symmetric square of gamma, so that this diagram commutes. So this map is, we just take a divisor of degree 2 and map it to the divisor class in the Picard group. And this map is clear and this map is clear. So I think there should be some very simple description of this map, but I don't have a candidate for it. So if somebody finds a candidate for what this map could look like so that this commutes, I will be happy. I've tried some obvious things and it didn't work. All right, so I would like to remember this action here, 1. And now we can proceed to the second part of this topic talk. So we can apply this, these ideas and this construction to Fano threefolds of type 4-1.
So could you please repeat what Picard tool is?
Yes, so we have the Picard scheme, which is the parameterizes the divisor classes on gamma, and we have a component of degree 2 divisors. And it's a smooth projective curve, which is non-canonically isomorphic to gamma. So the second part of this talk. So let me first define what the Fano threefolds of type 4-1 are. So we take a smooth divisor in P here V1 times here V2 times here V3 times PF V4. So this is just 4 copies of P1, but we would like to enumerate them so that we can keep track of them. And we take a divisor of a smooth divisor of degree 1, 1, 1, 1. And such divisors are known as Fano threefolds of type 4-1 or type X1111, depending on literature.
It's not an important question, but why it's called 4 and 1? So...
You also asked this yesterday when I prepared. But so the 4, it means that Picard rank is 4. So this is a lemma. And 1, I still don't know. But so it's just in this classification by Skorsky, and he enumerated them, and he said this is the first. I don't know why it's the first.
Something is the first, right?
So let X be the let's say
this part is not due to Skorsky, it is due to Mori and Mukai. Picard rank is due to Mori Mukai.
Okay, Skorsky is only rank 1. Okay, let X be such a threefold. So there are 105 classes of Fano threefolds, and they're all quite interesting. And this threefold class of threefolds is interesting in particular because there can be K forms of this threefold with Picard rank 1, and it's the last family of such threefolds for which rationality haven't been settled yet. So lemma 1. The Picard group of X is set to the power 4 and is generated by 4 divisors H1, H2, H3, H4, which are just the restriction of the degree 1 divisor from a P1 to this threefold. All right, and the main theorem, which is theorem in quotation marks, because there's a lot of details that still to be figured out, is that the Hilbert scheme of twisted quartic curves and such threefolds X is a isotrivial family over the intermediate Jacobian. So this is some elliptic curve which is uniquely determined by the geometry of X. And this is some isotrivial family. And all the fibers of this family
It's true that it needs to be an elliptic curve, but not an abelian variety. So it must be of dimension 1.
Yeah.
Okay.
You can look at the Hodge diamond of this threefold. It must be dimension 1. And it's isotrivial, and all fibers are isomorphic to X. But this is still theorem in quotation marks. And this is why, so by the first part of this talk, this is why we're interested in understanding the, it's also why we're interested in understanding the automorphisms of X, because such isotrivial families are naturally connected to such threefolds X. So we have two parts of the second part of this talk, part 2a and 2b. So in part 2a, we will discuss automorphisms of such threefold, and in 2b, we will return to this Hilbert scheme. Okay, so consider the automorphism group of X. If we have some automorphism, that automorphism will act on the set of generators of this Picard group by permutation. So we have a natural homeomorphism to S4. And for now, we are only interested in the kernel of this homeomorphism. So the automorphisms which act, which preserves each of the P1, so they don't switch them, which means that these automorphisms can restrict to each P1, so they act on each P1. So because we don't switch these P1s around, it's useful to consider the projection from X to, we have four such projections, so the first projection goes from X to P of V2 times P of V3 times P of V4. And it's a well-known lemma that this projection is a blow-up in a smooth curve of genus 1. This curve, let's call it gamma 1, because we can make this projection in 4 different ways. So it's smooth and projected, and it's a complete intersection of two divisors of degree 1, 1, 1. And yeah, but we could do, we have also gamma 2, gamma 3, gamma 4. Okay, and this curve is non-canonically isomorphic to the intermediate Jacobian of X. And we also have an exceptional divisor, E1, which is of multidegree -1. -1, 1, 1, 1. Okay. Now, because we are looking at the automorphisms, which doesn't permute these P1s around. What? It doesn't permute the V1, V2, V3, V4.
No, V4. There is some E1.
Исключительный дивизор. Yeah, the exceptional divisor of the blow-up. So this is some divisor on X. So an automorphism of X will commute with this projection, which means lemma 2 that the automorphism group, that the group G is isomorphic to the automorphism group of P1 times P1 times P1 to the subgroup of this group, which preserves the curve gamma 1. And you can show this using the universal property of blow-ups. And using this, we actually just need to understand how this group acts in the curve gamma. So this is the next lemma. Maybe that should be a
So that's what is the statement in this lemma? So we have set gamma and what we have set G. What we say about this?
Yeah, so this is the 3. The G, the group G, which acts on X, is isomorphic to the group of automorphisms of P1 times P1 times P1, which preserves gamma. So the image of gamma is gamma. It will act non-trivial on gamma, but it preserves the whole curve.
I think this is exactly the stabilizer of gamma, right?
Yeah. So theorem 1, theorem 2. The group G is isomorphic to the group of automorphisms of the curve gamma 1, which preserves the divisor classes. Yeah, so these divisor classes are important. I forgot to talk about them. We have divisor classes B1J, which is the restriction of the divisor class Hj to the curve gamma 1, but J equals 1, 2, 3. So these are some degree 2 divisor classes on gamma 1, which are important because they uniquely determine the embedding of gamma 1 into P1 cubed. And this group of automorphisms of X will be isomorphic to the group of automorphisms of gamma 1, which preserves these classes. 2, 1, 3, 1, 4. And the reason for this, I have 20 more minutes.
Yeah.
The reason for this is that so proof. So we have a resolution of the structure sheaf of gamma 1 as follows. It's just the Kosul resolution because gamma is a complete intersection. And if we tensor this resolution with say 0, 0, 0, then we obtain the exact sequence 0, -1, -2, -2, 0, 0, -1, -1 squared 0, 1, 0, 0. And here we have the restriction of 0, 1, 0, 0 to gamma 1. And if we take the long exact sequence in cohomology of this complex, we see that there's no higher cohomology here or here, here or here. And there's no cohomology at all. There's no global sections. And here we have only global sections. We have no higher cohomology, which means that the restriction gives an isomorphism on the global sections here to the global sections here. So the restriction gives an isomorphism between the linear system H. This was H2, but it could be Hj. The same works. by restriction is isomorphic to the linear system D1J. This one is because it's the curve gamma 1. We don't want to lose symmetry. And these linear systems are just P of Vj. It's just P1. So these are canonically isomorphic. And this means that if we have an automorphism J, so let J be some automorphism of gamma 1, let G be such an isomorphism that satisfies those things, then we can take the composition, let's call it Gj, from P of Vj to this linear system to this linear system. And then we apply this G, this automorphism. So because it preserves the divisor class D1J, it acts in this linear system. And this is some automorphism of P of Vj. Vj. And if we do this for V2, V3, V4, we obtain some automorphism G2, G3, G4 from P1 cubed to P1 cubed.
But on which statement are we proving?
That this is the construction, how given some automorphism of gamma 1, which preserves these divisor classes, here we obtain an automorphism of P1 cubed. And I claim that this automorphism preserves gamma. If you want to show this,
Are we proving lemma 3 using the theorem?
no, we are proving theorem 2. Lemma 3 I just stated. So we obtain some automorphism of P1 times P1 times P1. And if you try to write down everything more carefully, you will see that this automorphism preserves the curve gamma 1. And okay, now I don't want to write everything down, but given some automorphism of P1 times P1 times P1, which preserves the curve gamma 1, then we can just restrict this automorphism to gamma 1. And these two processes, this process and that processes, are inverse to each other. And this is the idea of this theorem.
I really have a question about lemma 2.
Uh-huh.
So you claim that the group of automorphisms would be the group which preserves literally the polynomial defining the stuff. But maybe it's the line of this polynomial.
Maybe what?
So a part of the stabilizer of the corresponding line might just multiply this polynomial by constant, and it will not change the variety.
No. PGL, so group of automorphisms of P1 times P1 times
Okay, so
P1.
you consider just this polynomial as a point in the projective space.
Yeah.
Okay.
Okay. So now we have this very concrete description of the group of automorphisms of X, which doesn't permute the P1s. And actually, using this, it's not hard to find the whole group of automorphisms, because then we just have to see how we can act on the Picard group, and we will obtain some semi-direct product of this group and some subgroup of S4. But using this theorem, can you see what G can look like? We have some, what can be some automorphism of this genus 1 curve, which preserves these divisor classes. Yeah. So these divisor classes all have degree 2. And so we are looking for some.
Why is it degree 2?
So
This is the restriction of divisors of gamma.
Yeah. To the curve gamma. You can look at this short exact sequence, and you can tensor with O1, 0, 0, and count the cohomology.
Mhm.
And you will see that it has degree 2.
Okay.
So basically some embedding of gamma 1 into P1 times P1 times P1, it's determined by degree 2 divisor, because we need a morphism from gamma 1 to the P1.
Mhm.
And that will be determined by degree 2 divisor. Okay, so we're looking for some automorphisms of gamma which preserves these degree 2 divisors. And yeah, so basically, if we have some torsion elements, as before, we have torsion elements, say T1, T2, and T3 in a peak 0 of gamma. So again, the translation subgroup of gamma, which acts by taking a point P and sending it to a P plus some two torsion element in peak 0 of gamma, will be an automorphism. And if we have some degree 2 divisor, then if that degree 2 divisor is represented by 2 points, say P, Q, then they will be mapped to P plus Ti, Q plus Ti. And their sum will be P plus Q plus 2Ti, and 2Ti is a 2 torsion element of peak 0 of gamma. So yeah, this way we obtain corollary 1, the Klein-4 group again, X on X. And when we restrict it to gamma 1, it acts by translation. So I don't know how familiar you are with automorphisms of elliptic curves, but depending on the position of these degree 2 divisors, we can obtain more automorphisms.
But that can be automorphisms that are not translations, right?
Yeah. So do you have some example?
Automorphism
Yeah.
is not translation.
Yeah.
You can take elliptic curve.
Yeah. Some elliptic curve. Yeah. So we also have the automorphism from gamma to gamma, for instance, which takes a point P and maps it to D12 minus P. And if a D12 and D13 and D14 are like tangent, if the tangents pass through D12, then this automorphism will also preserve all 3 divisor classes, and we can obtain more automorphisms. So in some special cases, we can obtain more automorphisms. But if these divisors are in general position, then this Klein-4 group will be isomorphic to G. But in general, we have an embedding into G. And when X is sufficiently general, this is an isomorphism. All right. And another corollary is that we can now construct an isotrivial family where all fibers are isomorphic to X, and we can do it as follows. We take X, intermediate Jacobian of X, and we take the projection to the intermediate Jacobian. And here we take the map, which takes P, and map it to the class 2P. So this is the class X. And here we take the quotient of X times the intermediate Jacobian of X by the Klein-4 group. And this gives some isotrivial family. And the claim is that this isotrivial family is in fact isomorphic to the Hilbert scheme of twisted quartic curves, which I will discuss now in the last 10 minutes. Yeah. this is part 2b of the talk. Okay, so first let's define what we mean by twisted quartic curve. So a twisted quartic curve on X is a curve, a rational curve of degree 4. And we are only interested in the rational curves which are not contained in a fiber of a projection from X to P1. And I don't want to define Hilbert schemes, but we have some Hilbert scheme which parameterizes all such curves. And the curve can be smooth, but they can also be singular. So it can be some union of some lines and conics that intersect each other. Okay, then the strategy is as follows. We have, if we take a twisted quartic curve, which is embedded into X, and we consider the projection to P1 cubed, then the image here, so this was, say, pi1, then the image pi1 of this quartic curve is a twisted cubic curve in P1 cubed. And we have two cases. Either the curve C will intersect the exceptional divisor E1 transversally, in which case this intersection will consist of 2 points, P1 and P2. Or this projection will contract a component of our twisted quartic curve, in which case so I1 contracts component. In the first case, then this twisted cubic curve, I1 of C, will intersect the curve gamma 1 in just 2 points, the images of these P1 and P2. In the second case, okay, it can be some length 2 subscheme of gamma, but if they're different, it will be 2 different points. Otherwise, the image, this twisted cubic curve, will intersect gamma in 3 different points, or some subscheme of length 3, actually, to be more precise. So the point Q will be the image of the component which is contracted, and P1 and P2 will be some points over which we don't have any components which are contracted. And actually, it's possible to construct some morphism. So lemma 4. There exists a morphism from the Hilbert scheme to the symmetric square of gamma 1, where we take the class of the quartic curve C and maps it to the class, to the P1, P2, to this length 2 subscheme. And this is a morphism. So the only way I know how to show that this is construct this as a morphism is using semi-orthogonal decompositions. Maybe if somebody knows easier way to construct morphisms from Hilbert schemes, but so far it's actually complicated to show that this is a morphism. All right, then we can take the composition of from the Hilbert scheme to the symmetric square of gamma 1 to P2 of gamma 1. So we take the divisor and we take the divisor class. Then this composition will be the Albanese map of gamma of the Hilbert scheme, which means that it's a sort of universal map from the Hilbert scheme to abelian varieties. And we can do this for each of the 4 projections. So we have the Hilbert scheme here, and we have 4 maps, 1 to symmetric square. How many minutes do we have left?
5.
Okay, symmetric square. Thank you. Symmetric square gamma 3, symmetric square gamma 4. And we have peak 2 of gamma 1, peak 2 of gamma 2, peak 2 of gamma 3, peak 2 of gamma 4. And basically, because the morphisms from the Hilbert scheme to peak 2 of gamma I, because peak 2 of gamma I is abelian, and because of some kind of universality, we obtain morphisms to the intermediate Jacobian of X, such that this whole diagram commutes. And the next lemma is that we obtain a closed embedding of the Hilbert scheme into this fiber product. So each of these is some P1 bundle over the intermediate Jacobian. So we can take the fiber product of each of these surfaces over the intermediate Jacobian, and this will be an embedding. So symmetric square gamma 1 fiber product over Jacobian of X of each of them. Gamma 4. And you can do everything very explicitly, and then to me at least it seems that the fiber, so we have a map here to symmetric square, no, to the intermediate Jacobian, the projection Jacobian of X. It seems to me that the fiber over this map, when I write down everything explicitly, is isomorphic to X. And I don't want to argue this right now, but basically let's call this thing for W. Then we already saw earlier that symmetric square of gamma to P2 of gamma was trivialized by a degree 4 itself cover, which means that we have a commutative diagram which looks like W here, and then W here, then P1 to the power 4 here, times the intermediate Jacobian. Then we have the projection. Here we have the itself degree 4 map covering. So this is trivialized. And the Hilbert scheme is a divisor here. And when we take the pullback, it just becomes the direct product between X and the intermediate Jacobian. W was just short notation for this fiber product.
Okay.
So the Hilbert scheme is a divisor in W, and W is trivialized by this itself 4 cover. And actually, I claim that the Hilbert scheme is also trivialized by this itself cover. And this is why this Hilbert scheme is very connected to the automorphism group of X. And I think this is all pretty nice. And I have 1 minute left, so maybe I can ask some questions.
What's the right arrow?
What arrow?
No, on the left side. From Jacobian to Jacobian.
Yeah. So this is multiplication by 2.
It's the same one. Okay.
Because this we saw in the first part that each of these symmetric squares were trivialized by this itself cover. So the fiber product should also be trivialized. And I can, anybody have questions? I have a question maybe. So. Yeah. Okay, maybe I should let you ask some questions.
Does anyone have any questions?
What's the question?
Okay, so the client 4 group also acts on X where we permute the P1 factors. And using this same construction, we can construct some family F here over the intermediate Jacobian of X. So this fiber product should be trivial. Where instead of using the action which acted, which didn't permute the generators of the Picard group, this action permutes the generators of the Picard group. then I think I'm right in saying that this family have a relative pk rank 1. So the generic fiber should be some form. So if we take the generic fiber, what is the right notation F0? I don't know. So it's some threefold over the function field of the intermediate Jacobian. And it should be some form of some final threefold of type 4,1 with pk rank 1. And so is it rational or is it not rational? A conjecture by Kuznetsov says that it's not rational, but
well, it seems that the technique developed allows you maybe to do a little bit more. So here you have considered the divisor of degree 1, 1, 1, 1. What will happen if you would consider some other integers? Well, positive integers.
You mean divisors of multidegree A, B, C, D?
So you can try to do similar things, just you have Jacobian, you can consider the divisors.
So you mean there should be some divisors of...
Maybe they are no longer Fano threefolds, of course.
Yeah, but they can be I think there should be some Villaro threefolds, which are divisors of, is there, of multidegree 2, 2, 2, 2, which are probably preserved by these automorphisms.
If the multidegree is 2, 2, 2, 2, then of course it is a Villaro.
No, but if they exist, which are preserved by the section, because to do this, they need to be preserved by the action and the P1 is. And maybe we can take some K family, isotrivial family of K3 surfaces by taking the intersection of two divisors of multidegree 1, 1, 1, 1. And this I'm pretty sure we can do, because we can pick different 1, 1, 1, 1 divisors which are preserved by this action. And the intersection should give some isotrivial family of K3 surfaces.